So here's the third lecture for Chapter 25. It's the last lecture for the course, and the last set of topics that I want to deal with are shown here. I want to go into details of a few functional groups for this course. Not all the functional groups that you'd come across in organic chemistry, but it's enough to get your feet wet for the subject. The last bit of nomenclature that I want to do is that for alcohols, and just like the other examples, we're going to use a systematic approach for it, and longest carbon chain, that kind of thing. So it's a new functional group, but new rules, not necessarily, just a few modifications to the old rules, really. And I do want to talk a little bit about chemical reactions, just 4 total, and there's going to be some overlap between the two subjects here with alkanes and alkenes. I want to get into one other type of isomerism known as chiral molecules, and then finally touch on a few topics from the first 2 presentations, really, with the practice exercises here, just as a little review of the material. The first functional group, first set of functional groups that I want to deal with is the concentrating on the oxygen atom and how many different ways can oxygen show up in an organic compound. And structurally, what's happening in some sense is that we're taking a simple molecule such as water, and we're modifying it. You know, if we think about water, this is a V-shaped molecule. It has certain. It's a very polar molecule. It can dissolve salts very easily. And what we do oftentimes in organic chemistry is to take, and this is actually how I teach it in the organic class. You sort of take your the notion that you have about a simple molecule and you start modifying it. For example, if I take one of these hydrogens off and then replace it with some kind of hydrocarbon unit, then I'm changing the chemistry just a little bit. This new molecule, which is this functional group, is called an alcohol, and is characteristic of just what you see here: a hydrocarbon unit and then one OH group attached to it. And depending on how long this hydrocarbon portion is, then alcohol is going to have a certain level of polarity that is analogous, maybe not necessarily similar to, but analogous to the polarity that you have for the water molecule. And so what you see in organic chemistry once you get into the subject is that a lot of times the physical and chemical properties of this guy mirrors a little bit of what you begin with in terms of what you know about simple molecules in Gen Chem. Now, of course, here we don't have time to go into the physical and chemical properties. That takes a 2-semester organic course, to tell you the truth. And really, all I want to do here is mainly introduce the functional groups to you, and have you be able to recognize the functional groups in a particular molecule. So again, an OH group that is attached to a simple hydrocarbon chain is referred to as an alcohol. If I was to take this structure and then replace both of the hydrogens here with some kind of hydrocarbon unit, and it doesn't matter if it's if it looks like an alkane or an alkene or an alkyne for that matter, it's still just a hydrocarbon unit. I mean, the chemistry is going to be different, but in terms of the name of the functional group, and in this one it's called an ether, then that's really all I want you to be able to do is to see, well, you have the oxygen molecule here, and there's 2 different hydrocarbon units attached to either side of it. Now, oftentimes in organic chemistry, for one of these hydrocarbon units, I use the label R as the phrase is an R group, and it's a generic label, just trying to characterize the functional group overall, and not getting into specifics about what each individual member of that functional group might do. Because again, depending on the length of that carbon chain, then it changes the chemistry of the compound. I guess length, and also the issues of how complicated is the branching on this particular portion of the alcohol or ether, for that matter. And so oftentimes what you see is that alcohols are abbreviated R group OH, and then an ether might be abbreviated 2 R groups on either side with an oxygen in the middle. And then sometimes you'll see a prime being applied to one of the R groups just to indicate that an ether can be composed of 2 different R groups on either side of an oxygen atom. For example, let me show you one here. So again, it doesn't matter. This particular example, this is like a symmetrical ether, the same group on either side of the oxygen atom, but the 2 R groups can be different. For example, here we have an ethyl and a methyl group on either side of the oxygen. Now, another very common, we'll say, carbon-oxygen moiety in organic chemistry is this guy. This is referred to as a carbonyl group. Now this carbonyl group, it's not a functional group. This is just a particular structural feature that's common to a lot of different functional groups, and you see it embedded in each one of the examples on this particular slide here. And notice that, depending on how you functionalize, either end of the carbonyl group dictates its chemistry, and again, for us, we want to just be able to recognize what kind of functional group we have in front of us. So here, if you notice, there's an ethyl and a methyl. I have a carbonyl group that's sandwiched in between 2 different R groups. This is referred to as a ketone. Here, we have an OH group and a R group attached to a ketone, and sometimes you see, actually, we've seen this particular functional group before. This is a carboxylic acid. And in this particular example, this is acetic acid, which is a 5% solution of acetic acid is vinegar. Here we have an R group with a carbonyl group, and then if a simple hydrogen is placed on one side, it's referred to as an aldehyde. And then finally here, what we have is we have an R group, and then notice that there is an oxygen between this carbonyl group and the other R group, and we can abbreviate this form as this guy here. And I'm going to go ahead and put a prime here just to indicate that the 2 R groups can be different, and this particular functional group is referred to as an ester. And so it's actually what's referred to as a derivative of a carboxylic acid. Just like back here, we take the simple water molecule and we start replacing, these hydrogens with something else, and that changes the chemistry of the molecule. Well, the same thing is going over here with the carboxylic acid. You remove that hydrogen, you place an R group on it now, and now it's an ester. You change the chemistry, you change the physical properties as well as a compound. And that runs through just about all of the functional groups for oxygen we need to know. There is an additional one on this slide here, and there's that carbonyl group. I'll get to it in just a minute. But this slide deals with 2 of the types of functional groups of nitrogen that you're going to find in organic chemistry. And again, when you look at this list, it's actually a short list of all the functional groups that you might come across in organic chemistry. I just really want to expose you to the simplest ones, the most common ones that will get you through this particular course, and then prepare you just a little bit for the organic chemistry that you might have to do later on. Now, actually, the 3 here, they're all in the category of something called an amine. And what we're doing here, again, if we go back to the simplest nitrogen-containing compound that we learned back in Gen Chem, something other than its elemental form, diatomic nitrogen. This is ammonia. Well, again, what we do here, just like we did with the water molecule back in the second slide of this presentation, you start removing the different number of hydrogens, and you start changing the chemistry. And that's what we see for these different compounds. We've actually come across some of these amines in the context of an acid-base reaction. Just like ammonia can act as a base when it's combined with an acid, well, any of these amines what we have is a lone pair electron on each of these nitrogens, and they can act as a base when in contact with an acid. And so in each of these cases, what I'm doing is I'm getting a more complicated amine as I start changing the number of R groups that are attached to that nitrogen. For example, here we just have one R group. Here we have an ethyl and a methyl R group. And then here, notice that we have an aromatic amine down here. Now for us, again, all I want you to do is to recognize that you have an amine in your molecule. And so nitrogen, when you see nitrogen in a molecule, there's two options, there's two possibilities. You have some kind of amine, or you have this guy down here, which is called an amide. And the chemical characteristic of amide is that you do have the nitrogen in there, and you can even functionalize the two hydrogens here. You can replace those two hydrogens with R groups if you want to, and you may come across that. But the main feature is that you have this carbonyl attached directly to a nitrogen. And if I expand the structure just a little bit around this guy, I want to do the expanded structural formula just around the functional group. This is typically how I do write it in organic chemistry. There you see that bond that directly links the carbon of the carbonyl group to the nitrogen. This is characteristic of an amide, and you see a lot of these in biochemistry, and we'll see some examples. You'll see some examples in the book. I don't think I do anything specifically here, but these are very common functional groups in biochemistry. And that really covers all the functional groups that I want you to worry about for this course. So here's a little practice exercise. There's 4 different compounds here. I would suggest pausing the video, go in here and pick out all the different functional groups you see, and then turn the video back on, and then I'll give you the answer. Now, first thing I want to say is that usually on this kind of question, the alkane label isn't really used. The only time you need to say that you have an alkane in front of you as the functional group is something like this, where it's a saturated hydrocarbon. That's really the only time when you see the alkane label being used for let's say a functional group. The reason why I mention this is because I'll start with, let me just start with this one here. This is a structure for testosterone, which is a human hormone that I'm sure everyone has heard and somewhat familiar with. What you have in there is one functional group that is related to the hydrocarbon talk from the first lecture for this chapter, and here we have an alkene embedded within this larger molecule. Now notice that we also have these. This is a polycyclic compound. I don't have to worry about you guys. I don't want to worry about you guys naming this as a cycloalkane. Again, we're just focusing on the anything associated with alkane. Just ignore in terms of a functional group on these more complicated molecules. Anytime when you see oxygen or nitrogen, don't worry about any kind of alkane label. But you do have a polycyclic compound. It's a combination of an alkene, and then these are saturated regions up here. The main thing I want you to do, focus on the different atoms that you have in your molecule. Use oxygen and nitrogen and double and triple bonds is what you want to focus in on when you're trying to label the different functional groups. Now, they're using the same convention that we established for simple cycloalkanes. Any point, any intersection of two or more lines indicate you have a carbon atom in here. And then that you can see it here. This is actually a carbonyl group. A carbonyl group that has 2 carbons on either side, 2 hydrocarbon units on either side, and it doesn't matter if it's a complicated polycyclic like you see here with a double bond, or the simple carbonyl group, the ketone that you had back here, with just an ethyl and a methyl. In organic chemistry, we describe both of these as, or we label both of them as a ketone. So just appreciate the fact that it really, it doesn't matter how complicated, at least in terms of naming the functional group, it doesn't really matter how complicated the hydrocarbon portion of the molecule is. You sort of focus in on that one particular region and look, locally, i.e. what's attached directly to that portion of that molecule that determines what the name of the functional group is. Ketone here. Up here we have an OH group. It's attached to a carbon. Single bond all the way around here. This is an alcohol. This is a very common sort of a structural motif for steroids that you find in biochemistry. Actually, all of my compounds here have a carbonyl group. So let's just take them one at a time. And again, focus in exactly, what is attached on either side of that carbonyl group. Here we have a carbon and then an OH group here. This is one of our carboxylic acids. And then the other functional group to worry about is a nitrogen. Again, oxygen and nitrogen. Use that as to sort of direct your attention. Any just sort of, combination of carbons and hydrogens, all carbon-carbon single bonds, you pretty much ignore in that particular portion. And then if you have some, more condensed region, don't worry about it as well for these molecules. Once you get into organic chemistry, you can worry about it. So remember, for the nitrogens, we have two possibilities. We have these amines here, or if the nitrogen is attached directly to the carbon in the carbonyl group, then we would call it an amide. Well, what do we have in this example? This nitrogen is attached to a carbon. This is not the carbon of the carbonyl group. Even though it's close, it's not directly attached to it. Therefore, we'll want to call this an amine. Whereas this example down here, we have the carbonyl group, we have the nitrogen there. They are attached directly beside each other. And that's the other functional group for nitrogen, the amide. Notice if we scan this molecule, there's, that's what should come out at you. There's another nitrogen. How is it bonded? There's no carbonyl group attached directly to it. And so for us, we can safely say this is an amine. And that is true. There's a carbon up here. We have the geometric structure shown for the cyclic structure. And remember, each corner here, each intersection of two or more lines indicates just another carbon atom. And so this is consistent with the amine formula. And then finally, there's our carbonyl group again. Again, two simple carbon-hydrogen units on either side. This is a ketone, analogous to that ketone there. And then the other functional group that we haven't seen in the last presentation, I don't believe, is this guy here, and that is a haloalkane. So again, some other atom besides carbon and hydrogen is what you should focus your attention on when you start tracking down these functional groups. The only carbon-hydrogen functional groups to worry about would be an alkene here, or if you saw a triple bond in the molecule, you would want to label that as an alkane. I do classify those as, or I do want you to label those in a given molecule as well. But that's your, expect something like this on the test, the last test for this course. Some molecule, and I'll ask you to just simply label the functional groups that you see in front of you. Again, all I'm trying to do is sort of prime your pumps, if you will, trying to get you exposed to some of the basic concepts that you'll come across in organic chemistry. Now, this example here, this is the last nomenclature example. Now, every single functional group that we just looked at, has its own set of rules for naming the guy. And so, but it's all based on that systematic approach that we established in the first two presentations. Now, we're not going to cover every single functional group back there. The only one that I really want to worry about is the alcohol functional group. And here what we do is this this first rule here, it's actually similar to what we saw with the alkenes and the alkynes in that last presentation. This idea that the functional group can tell us, where to begin our process in terms of naming the compound. We're going to name these using the systematic approach, like all of organic chemistry. We're going to number the longest carbon chain, and I'll go ahead and do that. Just like with the alkenes and the alkynes, we use our functional group to sort of direct our attention here, so that we can find where we start numbering the longest carbon chain. Now, one reason I wanted to throw this example at you is because there's actually two functional groups in this particular molecule. You have an alcohol here, and then you have a haloalkane here. Well, simply put, we are going, even though this is a bona fide functional group in organic chemistry, we ignore it in terms of the longest carbon chain, at least in the sense that we see here. It doesn't dictate how we number the longest carbon chain, except for except in the context of what you saw in the first presentation, meaning that if this thing was like on just a simple haloalkane with no alcohol functional group, then this would treat as just another substituent group. And that's the role that it plays in all nomenclature. So what we see here is we have an alcohol, we have a functional group that wins out. This thing trumps the haloalkane here, so it establishes the longest carbon chain from the perspective of this particular functional group. And then the bromo is just named as another substituent group. So you have one bromo at the number 4 position. I'm going to go ahead and put that in. That establishes the prefix. What are the substituent groups doing coming off the longest carbon chain there? And then the last part, the parent name here, what is it doing? It's telling us, well, how many carbons. In this case, we're going to have a hex or hexa base name from our list here. Remember, we're still going to use these guys, 6 carbons for the longest carbon chain. And then the systematic approach that you find in IUPAC is that the suffix is telling you what the functional group is here, and the ending that is placed on all molecules that have this alcohol as a functional group in there is an OL at the end. Let me put that together here for this example. And so notice that what happens is that if we had a 6, well, let's just go back to this diagram here, this table. If we just had 6 carbons as a straight chain alkane, we would name it hexane. Well, what we do is we replace the E on the end of that name and then add an OL to it, so hexanol. I've indicated the 1 here just to establish where on the longest carbon chain the functional group is actually showing up. And so the 1 in front of the parent name is telling us, again, where on that molecule is the OH group, because really that OH group could have been at any position along the longest carbon chain, and this number would have changed accordingly. For example, on this guy is another good example. Again, we focus in on the functional group here to establish the numbering procedure for this particular compound, and we're still looking for the longest continuous carbon chain. Now, I'm just going to go ahead and number this so you can see it while I talk about it. Notice that I still number the longest carbon chain. That longest carbon chain, the OH group is attached directly to it. I don't have to begin the number 1 label with the carbon that's directly attached to the OH. Okay, so the game is still finding that longest carbon chain, but this time, we try to get that OH group, somewhere on that longest carbon chain. And then what we have, we've established our parent name here. Number 2 position, there's a lot of branching going on here. There's the alcohol functional group that is there, and then we also have this methyl substituent group. Let me put that name together. It's 2-methyl. That's your substituent group. And then remember the form of the name here. There's a numerical value in front of the parent name, and that establishes where the OH group is coming off at. And it's coming off at the number 2 position on a 3 carbon chain. So prop is used as the base name there. And then to complete the name, it's propanol. And there you have the OH group here. And so whenever you see an OL and then an A there, it tells us that you have, an alcohol on a longest carbon chain with just single bonds in there. Now, this is really as advanced as we're going to get for naming alcohols. If you get into organic chemistry, you'll see alcohols being thrown onto alkenes and alkynes, and then actually what you see here is that letter changes. If there's a double bond somewhere in the molecule, you see an E placed in that position. But again, we're just going to deal with carbon-carbon single bonds. We're not going to mix functional groups in this class. The only mixing that you're going to see is that maybe one of the halogens might be thrown in with alcohol, but other than that, the alcohol is going to be by itself on these molecules that you have to name. Okay? And that pretty much does it for the nomenclature we need to worry about. Into this presentation, there'll be a few more practice exercises just to review what we've already learned. Okay? Now, in a 2-semester organic class, there are dozens of reactions that you have to learn. I don't think it pushes 100, but it may be close. In the broader scheme of things of organic chemistry, there's thousands of chemical reactions. And do we have time for that? Of course not. What I want to do is just expose you to a few examples. 2 are shown here: combustion reaction and a halogenation reaction. And actually, that's just about all an alkane is going to do. An alkane burns, and then an alkane can be halogenated. So you see sort of embedded within there, that means that for us, we're going to be placing either chlorine or bromine onto the molecule. So let's look at these reactions, so give you some exposure to it. I'm going to take, this is a saturated hydrocarbon. Notice the ratio here. It's this kind of ratio. So that means that I have an alkane in front of me. And so what you need to do, and you've seen this before. It's been maybe a long time, but Jenkin 1, Chapter 5, combustion reaction for hydrocarbons. And what you're responsible for is this would be the kind of question you would be given. Show the balanced chemical or the balanced combustion reaction for this compound. So everything else from here on out, you would have to provide to me. We now see a combustion reaction. What's happening? It's a reaction between the hydrocarbon and just oxygen, and then the only 2 products you get: carbon dioxide gas and then water vapor. And then I want you to balance this thing, and the procedure for balancing this particular reaction is the first thing you'll want to do is balance the carbons and hydrogens, and then save the oxygen as the last step in the balancing act. What's going to happen? Well, let's just see what happens. If you do carbon and hydrogen first, what you do is you see there's the carbons and hydrogens are going to be counted up from the hydrocarbon portion of the combustion reaction. There's 5 here, and there's 12 hydrogens. I can balance out those 2 by placing molar coefficients of 5 and 6 in front of the carbon dioxide and the water. So 6 times 2 gives me 12 hydrogens on both sides, and then 5 times 1 gives me 5 carbons on both sides. So by saving the oxygen for last, well, what's going to happen is that typically you can put 1 coefficient in here, and you can balance out the oxygen without affecting the count for the carbons and hydrogens. This is a typical kind of balancing act. Like I say in my classes, when you're balancing a chemical reaction, by the 2nd or 3rd step, everything should start to converge. Everything should start, falling into place. If you get to step 7, that means somewhere along the way you've gone the wrong you've taken the wrong path. So 1, 2, this is my third step along the way. And so to count up the oxygens, let's say I have 2 times, I have 10 oxygens from that guy, and then I have 6 oxygens from the water molecule. So there's 16 total on this side. Notice that there's a 2 for the oxygen. What times 2 equals 16? Well, that's simply 8. And so now I have a balanced combustion reaction in place. And that's all you would need to give me for that, actually. The halogenation reaction, what you're going to see for it is actually you're going to see not just a molecular formula here. You're going to be given a condensed structural formula, or like I have here. Typically when I draw something, I use a mixture of expanded and condensed structural formulas. And then the reaction that you see for the halogens, and I'm going to do bromine here, but everything I say about molecular bromine can also be applied to molecular chlorine. So either one of these reagents will work for this halogenation reaction, and the same thing is can be said for the alkenes as well on the next slide. Just a comment about the use of the arrow here. This is a little technique that I always use in my organic class. I use the arrow above and below the arrow to establish the reagents and the conditions needed for the reaction. So when you see the H nu there, what that means is that there's light energy being placed into the system. That acts as an activator to get this reaction started. And what's going to happen is that we are going to replace one of the hydrogens here. In this particular example, it's going to be that one, with the halogen, whichever one we choose, bromine or chlorine. And then that completes the halogenation reaction. Honestly, a lot of times for these reactions in organic chemistry, I don't worry so much about balancing the reaction, to tell you the truth. If I'm doing a reaction mechanism in the class, I account for every little thing. But if I'm just trying to keep track of what happens to this particular functional group under these conditions, usually it's just that particular product of interest that I'm concerned with. Some minor products that are being formed from the breakdown of the reagent, I'm not so concerned with for this particular example. These halogenation reactions, there are a few rules that I talk about in my organic class that I'm not going to worry about here, honestly. All I want you to be exposed to is the general idea that a reaction occurs between an alkane and then either one of these halogens, as long as there's some extra condition like light, and actually another reagent that would work. You can give heat to the system to cause the same reaction to occur. So keep that in mind as well. Heat or light will be used for causing this reaction to occur. There's actually rules in terms of where the bromine actually shows up on the molecule, because I could have chosen any of the 10 hydrogens here to form the product, and I chose this one because that's typically what happens for a bromination reaction. But I'm not worried about that. All I want you to do is to be exposed to the chemical reaction and know that just choose one of the hydrogens to be replaced with the bromine or chlorine, and just show one of the products that can be formed from this particular reaction. The reactions for the alkenes, well, in some ways they're a little simpler, in my opinion, and that's one reason why I want to show this is to get the idea across that when you have a functional group in your molecule, well, what did we see in the previous examples for nomenclature? We saw the functional group dictating how we name the compound. It told us how we started numbering the compound and laid out the parent name. Well, there's some similarities with that in the chemical reaction. It's the functional group that always gets beat up upon, if you will, in a chemical reaction or in organic chemistry. For example, the two here, these are both referred to as addition reactions. And what happens is that whether you have bromine, molecular bromine, or hydrogen gas reacting with an alkene, what happens is that the bromine atoms and the hydrogen atoms add across the double bond, breaks the double bond to a single bond, and now you have the new product where, if we expanded the structural formula here to see everything, that's what it looks like. Bromine has taken the place of the two hydrogens that would have been here for like a saturated hydrocarbon. It's a method to actually, this synthesizes haloalkanes. Another example. I guess the previous halogenation reaction worked as well. But again, one thing we see is that it's the functional group that is more reactive. Like I said, what do alkanes do? Alkanes burn, and then alkanes undergo halogenation reaction. That's just about all we see them doing in organic chemistry. Once you start throwing in other functional groups, then you start expanding into a much broader picture in terms of chemical reactions that can occur. And I've only chosen two of the simplest addition reactions, just again to get you exposure to what's happening in this very broad field. There are at least a half dozen simple addition reactions that you would get a hold of probably in your first semester of organic chemistry, and these are just two of them. The hydrogenation reaction down here, what's happening here is that you have a double bond in this ring system, and I'm going to draw in the other hydrogens around this ring system, since it's been, I guess, it's just the first part of that second lecture where I actually talked about this subject. Remember this, from this portion of the ring system, you have, essentially a saturated hydrocarbon where there's a carbon. Anytime there's an intersection on the cyclic structure, that means we have a carbon there as well as here. And then we fill in the number of hydrogens needed to complete the valency for the carbon. And what do I mean by that? Well, let me not put hydrogens. All that means is that valency is 4 for carbon. Think about your Lewis structures back in Gen Chem 1. You always saw carbon with 4 bonds around it. Well, over here with a double bond, if I'm looking at this particular carbon here, it's got 1, 2, 3 bonds shown explicitly. The fourth one is out to the hydrogen. Now, once this reaction proceeds forward, what happens is that, just like with the bromination up top here, we're getting whatever the diatomic species is that reacts on this double bond, those two atoms are spread out over the two carbons of the original double bond. And it forms a saturated hydrocarbon now. The last thing I want to say about this is typically there is a metal thrown in the mix as a catalyst. This is a heterogeneous catalyst is what we have here. It was talked about in chapter 14, just a little bit at the end of that chapter on chemical kinetics. Another nickel is another one that you see for the metal, and then palladium. Those three tend to be the most common ones that you see in organic chemistry. So that is an additional feature that I want you to add to these chemical reactions. Platinum, nickel, or palladium is needed as a catalyst for these reactions. And again, all we're looking at is the overall recipe. We're not getting into like the mechanism of how this happens. That really you can only cover. You need a 2-semester course to be able to cover that kind of material. And that's really all the chemical reactions that I want to look at. Just 4 out of the thousands that's out there for organic chemistry. Just a little exposure to the material. Now the next new topic for this particular presentation, I guess it's the last new topic, I believe. is dealing with it's an extension of what isomers are. Now this is a slide from the second presentation, just reminding you of what constitutional isomers are. Now all isomers have this feature, same molecular formula. Constitutional isomers, different connectivity. So you can see here the carbon backbone is broken down into different patterns, and it becomes slowly more spherical as you go across the slide here. That's one type of isomer, constitutional isomer. Another one that we learned for alkenes are the stereoisomers. And without getting into a more specific label, I'm just going to use stereoisomer as to label the cis trans here. I'm not going to get any more specific than that. And the main thing here is that, you know, the point of difference between the two molecules, it's not the molecular formula, it's not the connectivity. The connectivity is the same. All it is that there's a difference in the spatial arrangement. And then again, for the double bond, remember when you have a double bond here, this is locked into place. And so there's no free rotation between these two carbons here. And so what happens, you can establish these two different patterns with the hydrogens, or you can even think about the R groups on being on the same side here. But typically for this class, I like just to focus in on the hydrogens because that's what's going to be common in all the cis-trans nomenclature that you have to worry about. There's actually one other type of stereoisomer. This stereoisomer label here, this is a rather broad category, if you will. There is a specific term for this one, but I'm not going to worry about it. The specific term that I want to use here is that guy. So we're still talking about stereoisomers, but now I'm going to put a finer edge on the type of stereoisomer that we have in front of us on this example. The reason why I want to talk about this one is it's very important for biological systems. Essentially, every molecule in your body, just about, is some kind of enantiomer. And this topic of stereoisomerism plays a very important role in terms of the biological sciences and allowing some of the chemical reactions that you see in your body. And the main feature for the enantiomer, well, we'll notice that I have the same set of definitions here under stereoisomers as we saw on the last slide for cis-trans isomerism. Same molecular formula, same connectivity. This different spatial arrangement is still true. Now the difference in the spatial arrangement here is simply that the two molecules here are mirror images of one another. Okay? Now what I mean by that, it's a little hard to get across probably in this video lecture, but you're actually carrying two enantiomers with you right now. It's actually your left and your right hands. Do this experiment. Go to the bathroom, go in front of the mirror, place your left hand in front of the mirror and look at the reflection in the mirror. What you're going to see, you know, if there's my mirror here and my left hand is out here, the reflection in the mirror is actually equivalent to my right hand. Try it. You'll see it. Now, and you can do this without being in front of the mirror, try to superimpose your left hand over your right hand. There's no way that your left and right hand can overlap exactly. You know, try putting a right-handed glove on your left hand and you'll see that it doesn't fit. And so this is what the term chiral means, is that you have two mirror images that can't fit on top of each other. And the way we recognize a set of enantiomers in organic chemistry is simply, and look at our ball and stick model here. These are two carbon atoms here. And then there are 1, 2, 3, 4 different molecules or 4 different groups attached to that one carbon atom. That's how you identify an enantiomer in organic chemistry. For us, there's this subject can deal. You can cover. It requires an entire chapter to deal with this subject in organic chemistry, and we're just looking at really 2 things: what is the definition, what is the concept, and then how do we recognize an enantiomer in our in a molecule that we're looking at. The term here, this is referred to as a stereocenter. And again, to find that stereocenter, it's a carbon with 4 different atoms or groups of atoms attached to it. Again, that's the only thing we're looking for enantiomers. Now, in class, I'm going to bring in 2 models to illustrate this more effectively. But when you have this particular layout, well, if you were to make a model of this structure here and place it in front of a mirror, and this is trying to represent a mirror, the reflection you see in the mirror is actually this guy here. And again, I'll show this in class, and we might get a chance to play with the models just a little bit. But these 2 molecules cannot be superimposed on one another. They're like the left and right hands. Again, there's no way that you can place your left and right hand on top of each other where they completely overlap. It just doesn't happen. A pencil you can do that with. A coffee cup, usually you can do that with. But chiral molecules, enantiomers, hands, you cannot do that with. Another example, same definitions up here, just another layout, a different molecule. This is a ball and stick. We haven't seen these in a little bit, but I do want you to be at least a little familiar with what you're looking at. Again, the black spheres are the carbon atoms, the gray is a hydrogen, and here's a new one, the bromine there. And what we see is that, well, actually, let me name this thing. 5-carbon chain. Number 2 position, there's a bromo group, so it's 2-bromopentane is what we have here. Two-bromopentane is a chiral molecule. And the way we can recognize that is this one carbon here. It has a hydrogen, it has a bromine group, it has this group here, and then it has this group here. Actually, this is a CH3 group. That's a methyl group, and then this guy is a CH2, CH2, CH3. It's actually a propyl group coming off on this end here. We don't use it in the nomenclature, of course, but we use it in the sense of just identifying those 4 different atoms or 4 different groups of atoms that are attached to that one carbon. And again, when we see that, then we say, well, this is a stereocenter, and then we're going to have the mirror image of it is non-superimposable. There's no way that you can fit this molecule exactly over top this molecule. There's always going to be 2 groups that are out of place when you do this. When you look at biological systems and enzymes acting on substrates to form some kind of product, you see stereochemistry, enantiomers playing a major role in that kind of reactivity. One example is something called thalidomide. It is a molecule that was used back in the 70s to help reduce morning sickness in pregnant women. Well, as it turns out, the drug that was actually manufactured was a mixture of 2 enantiomers. And what happened was that one enantiomer would actually help with the morning sickness, and it didn't have any adverse side effects on either the mother or the fetus, but the other enantiomer caused birth defects to occur because what it did is it interfered with the development of the fetus, and as a result you had a lot of strange birth defects from children whose mother had taken thalidomide back in the 70s. You know, one of the nice things about recording this in my office, I just did a quick search on thalidomide, and I found a set of archives, some radio broadcasts from back in the 60s and 70s, it looks like, and there's some old television footage as well. If you're curious, do a search on thalidomide, and you'll see what I mean by the birth defects. It's not, if you're, well, you should look. Actually, it's some of the pictures I find disturbing, but it certainly brings it home in terms of the importance of making sure that the drugs that are being taken are that you know what is in there. And to me, it brings impact in terms of the importance of this stereoisomerism issue. Again, one isomer of the compound worked fine. It's the other isomer that gave problems, that caused these birth defects. And when they actually produced the drug, then it was a mixture of the two enantiomers that was actually sold, and so that's what was causing the problems. So if you're curious, take a look at that and just see for yourself. It can be, I find it pretty dramatic, some of the pictures there. Now, what our job here is to just recognize what we're looking at, recognize examples of enantiomers. I'd pause the video again. Each one of these molecules has at least one enantiomer, and go find it, and then restart the video. Now, the examples for alanine and valine, these are actually amino acids. Like I said, if you take biochemistry, stereo isomers show up everywhere. Now, you may not necessarily, as you go through organic chemistry and you start learning about all the issues about of enantiomers, you won't necessarily use all of that information in biochemistry, some of the nitty-gritty details there, but it's still, they play a role in any kind of, almost any kind of biological reaction, especially those involved with enzymes. And the reason why I brought in valine and alanine is because, well, they're building blocks for proteins in your body. And of the 20 or so amino acids that's used for forming proteins in your body, there's only one that's not a chiral molecule. All the others are. And the carbon that is the stereocenter for amino acids is referred to as the alpha carbon. You're not responsible for that, but I do want to use that label because that's something that I'll use here. So it's these alpha carbons, and what you see on each of the alpha carbons is that there is, well, just like there's 4 different things attached to it. And I'll just do the case for alanine here. Remember, it's not 4 different atoms, because I mean the carbon and the carbon are the same here. It's what is attached to each of those carbons that dictate that you have a different group. You have this what's called a carboxylate group here, and then you have a methyl group here. And you see there's 4 different ones here. So if you drew a 3-dimensional structure of this, then its mirror image is, again, non-superimposable on itself. And in class, I'll bring some models in to illustrate this better, because I really can't do it here on the video lecture. But I can, go through some examples and have you pick out the stereoisomers or stereocenters in these molecules. One thing to look for, so actually what not to look for, to tell you the truth, aromatic rings in red here, just ignore these. Notice that there's 2 different uses as indicate the aromatic ring: alternating double single bonds on a 6-membered ring, or you have this ring in the middle. That's something to ignore. A CH2 and CH3s you can ignore, and then any kind of double bond or triple bond are not going to be stereocenters. Okay, so that really leaves like in these examples, it leaves well, this carbon and that carbon there. This carbon, if you have 2 methyl groups, 2 are the same, and so it's not a stereocenter. This is the only one that's the stereocenter in this molecule. There's this guy, the methyl group, this carboxylic acid unit, hydrogen, and then the rest of this molecule over here, the 4 different groups around it. Same thing over here. There's one, there's the second one, there's the third one, and actually the convention here is that there's another hydrogen in there. I'm not going to give you, when you see these molecules on the test, I'm going to show all the atoms. So I'll write the carbons explicitly here. I won't do anything like this to you. I just wanted to give you another exposure in terms of what is out there. But again, 4 different groups on the same carbon, you have a stereocenter, and you can have a set of enantiomers. And that's really about as far as we want to go. And then I guess the last thing I want to just remind you of, just know the definitions. We have mirror images of one another that, like the left and right hand, they can't be placed on top of each other exactly. And again, that's best shown in class. So this is really the last topic for the chapter. The rest of the slides are practice examples. So here's one, the hybridization exercise. And for each one of these, so I don't repeat it every time, each new slide I would pause, try to do the exercise, and then turn the video back on and see how you did. So what I want to do here is, well, the hybridization of just the carbon atom. That's the only one that I really care about. And then also I want to add something else. Any chiral carbons or stereocenters. Both of these two terms are equivalent. So stereocenters is the one that I'll try to stick with from here on out. First off, let me do the stereocenters. Again, we're looking for a carbon with 4 different things around it. There's 1, 2, 3, 4 bonds on this carbon, and you see this is actually an amine group here, because that blue is a nitrogen. That's an amine. Over here this is actually a carboxylic acid. I won't hold you to interpreting that information. There's a hydrogen, and then there's another carbon and another unit. So this is actually the stereocenter, the only stereocenter in the molecule there, that carbon at that point. Now in terms of hybridization, now remember hybridization is dependent upon the geometry. And let's see, let me do in red. Well, maybe that's not. Let me change that. In red, let's do the sp3 hybridized carbons, which are these two here. Remember, sp3 hybridized carbons can be recognized if you have a tetrahedral geometry, and you do have it in both of these examples. So the stereocenter, I've already pointed out the 4 bonds around it. This carbon, there's 2, 3, 4 bonds with that carbon, so it's an sp3 hybridization on each one of those. In blue, let me show the other hybridization that I see here, and it's all the other atoms, all the other carbon atoms, I should say, and these are all the ones in blue are sp2 hybridized. They are trigonal planar. And the way we see that is there's 1, 2, 3. It's a flat structure here as well as here. And so it indicates that these are sp3 hybridized atoms. There's an approximately 120 degree bond angle there, and then back here for the tetrahedral there's a 109.5 degree bond angle all the way around that carbon atom. That's a typical exercise that I would want you to be able to do for the test. The next one, the reminder for naming alkanes. Since we haven't seen it in a while, let's take a look at it. First off, you want to find the longest carbon chain. That's the first step for naming alkanes. Remember, there's no double bond or triple bond or alcohol functional group here, so we sort of have to go searching for our longest carbon chain. And we have to number that longest carbon chain based on the branching. So number LCC based on branching pattern. We'll see if that helps. And I'm just going to do this, as if I've never seen the example before. And so, what I see here, this is probably the longest carbon chain at this point. I'm pretty sure that's right. What's the best way to learn these? Well, to do practice on them, of course. I'm going to number, well, let me just go ahead and really mess up this drawing. Let me number it both ways and see what we get. 7 carbon atoms. So I know, at least I know this part. I know heptane is going to be the parent name. I just don't know exactly how to number it, because if I start at this end, the first point of branching is that number 4. If I'd start at the other end in red, and let me do it within the carbons now, 1, 2, 3, 4, 5, 6, 7. Obviously I still get 7 carbons, but then notice here the first point of branching is actually at the number 3 position. And so the red is going to win out in terms of numbering the longest carbon chain. Remember, you number from the end that's closest to a substituent group. And so now once I know that, then I know how to establish the numerical values for laying out my substituent groups. I have 2 methyl groups, so one's at the number 3 position, one's at the number 4. 3,4 dimethyl. Remember to throw in your Greek prefixes there. And then the parent name is simply heptane. And by doing this, oh, actually I see a mistake. It's not unusual. There's a 3rd methyl group. Well, I can fix that. And this is an excellent example, actually, because you got 3 methyl groups. Yeah, I'm going to have a trimethyl in front here, but what about the numbering? Well, remember, at each substituent group needs a unique number, so 3, 4, 4 is actually what you're going to see, oops, in the front part of this name. Okay, so remember, the 3, 4, 4 tells me, it's not a redundant statement. 3, 4, 4 trimethyl, this is not redundant, it's being very specific. It's telling me I got 1 methyl group here and I got 2 methyl groups on this carbon here. If I just had trimethyl heptane, those 3 methyl groups could be placed really anywhere in between the 2 end carbons, and you would give rise to a different constitutional isomer actually at that point. And so the use of all the numbers is very important in terms of getting the proper name and structure across to whoever you're communicating this information to. Alkene nomenclature, and the next one is alkyne nomenclature. Now, fortunately, just like with the alcohol nomenclature we saw in this presentation, we have a functional group in our molecule. And so, when you have a functional group, then the long carbon chain is numbered based on the functional group, which is convenient, to tell you the truth. If I can see the longest carbon chain in this particular molecule, it's along the horizontal on the slide. This end is much farther away from, without even numbering, I can tell that this end is much farther away from the functional group. So it tells me that I need to number from this end. Okay, so I have 8 carbons. The octene is going to be my parent name. I have the double bond at the number 3 position, and then the methyl group at the number 6 position, and that accounts for both the position of the functional group as well as there's only a single substituent group in this example. Let me put that together. Remember, there's our prefix, the substituent groups in front. That double bond could have been really any place along the 8 carbons here, so I need the 3 in front of the parent name to be able to establish exactly where am I looking on this thing. Where is that double bond? Without the 3 there, then it becomes unclear, becomes vague, too vague for us. We can't draw the structure without the 3 there. Now remember, whenever you're dealing with an alkene, you got to worry about your cis-trans label. And here we see our 2 hydrogens on the same side, and we use cis in front. And remember, cis goes out in front of the entire molecule, like we see here. And then there's a hyphen between the cis and then the rest of the name for the molecule. I guess the only time when cis-trans isn't used for us is if, let's say, in an example like this guy. if you have the double bond between the 1 and 2 carbon, you don't need to worry about cis-trans, right? Because there isn't. If you break this up, if you look at this end here, and that is ethyl group up here and a hydrogen there. You know, with the 2 hydrogens there, it breaks that problem up. There is no there's no way you can draw this molecule to where you have that different spatial arrangement when you have the 2 hydrogens on the end there. And that's the only time when you don't need a cis-trans. Cis-trans mean nothing for an alkene where there's a double bond at the very end. If you take the organic chemistry, there are issues well, actually even there, if there's 2 hydrogens, you don't have to worry about any kind of descriptive term like cis-trans. But in the organic chemistry, you would also maybe introduce a bromine or OH group in this guy, and if that's on the end, it can give rise to a different type of label for these double bonds. But that's not important for us. Just cis-trans for double bonds that are actually within in the interior portion of the alkene. Last example, the alkyne. Again, we still have a functional group, so fortunately we can use that as establishing our longest carbon chain. And here, since it's on one end, then it automatically gets the 1 position. 3, 4, and then at this point I have a branching point. I have to decide where's my longest carbon chain. Well, the methyl groups don't work here. It's 5, 6 going up here. And so again, typically for the examples you're going to see is the longest carbon chain isn't necessarily going to be drawn along the horizontal of the page. So please keep that in mind. So I have a 6-membered or a 6 carbon longest carbon chain. Have an alkyne at the number 1 position, and then both at the number 4 position I got 2 methyl groups. There's my substituent groups. That's my prefix here. I'm going to go ahead and put a 1 in here for the position of the triple bond. And then I have 6 carbons gives the hex, and then the YNE gives the ending on the name to tell me I have a double bond. Triple bond. Last thing I'll say is oftentimes, like for us, number everything, and then you won't have any problems. When you get practice with this, actually, a lot of times you can just leave the 1 out of this, and it's sort of assumed that it's in that position. It doesn't really bother me too much. But for this class, number everything. Number the position of the functional group, number the positions of the substituent groups, and you won't have any trouble with the nomenclature for this course. And that does it. That's all. Thanks.